Welcome, Smashers. It's great to see you again. We're so glad that you joined us, and I hope that some of you listening today were able to join us at our first Smashers Live in Dallas at our Hope Summit a couple of weeks ago. We had so much fun, and it was such a joy to host each of you there. Our speakers were phenomenal, and maybe if you weren't able to join us live, you may have heard some of our sessions virtually. But if you have not able to listen to those or were not part of our virtual sessions, then I want you to know that all of those sessions that were recorded and live streamed are now available at our website, which is, as you know, longevity.org. And if you scroll down in our small cell lung cancer gateway to our section that actually says latest updates, you will see links to all of the live streamed sessions, not only the Smashers live sessions, but also the sessions from Hope Summit. So hopefully you'll get a chance to listen to some of those. We're going to have a great conversation today. Dr. Shields, would you like to introduce our guest?
Thank you, Anne, and thank you to all of our Smashers listening in. Welcome and happy Friday. I have the honor and privilege of introducing a dear friend and a phenomenal researcher, Dr. Simon Heeke, today. Welcome, Dr. Heeke.
Thank you for being, Thank you for the invitation. It's great being here today.
Wonderful. We're excited to have you. I think our Smashers are going to really learn a lot and take a lot back home to their teams after this conversation. Dr. Heeke this is a tall order to put his intro into we could have a whole hour, I think, on his intro alone. He is a former head of the Liquid Biopsy Translational Working Group and an assistant professor in the Department of Thoracic, Head and Neck Medical Oncology at MD Anderson Cancer Center in Houston, Texas. His research, which is vast, focuses on biomarker development and precision medicine, specifically in small cell lung cancer, as well as oncogene-driven non-small cell lung cancer and head and neck malignancies. He is developing tissue and liquid biopsy-based biomarkers through the integration of multimodal data and the use of machine learning for clinically applicable predictive models. He has contributed to over 80 peer-reviewed publications in various high-impact journals, and he serves as the co-chair of the NIH Liquid Biopsy Scientific Interest Group and co-leads the module on novel technological development in the European Masters in Molecular Pathology. A well-accomplished, well-recognized expert in the field. We're so excited for you to be here. Again, welcome, Dr. Heeke.
Thank you very much for the kind introduction. It's really a pleasure here. I was mentioning, I really like those discussions and always try to join them. And even I learn a lot from all the webinars here. So it's really an honor to be here today.
Thank you. And thank you for all of your work for our Smashers and really advancing the field. So without further ado, let's get into our discussion today. So let's kind of lay the foundation, lay the groundwork, right? So for our Smashers who might be newly diagnosed, listening in, all of the science, obviously, it's a whole new language. This can feel very overwhelming, right? It is when we had Dr. Christine Lovely on our Smashers, goodness, what Anne, about a year and a half ago, it was like you need a language guide as part of your diagnosis, right? And so, can you kind of tell us what are the tests that really provide knowledge that this is a small cell diagnosis? What diagnostic, molecular, how do we get here?
No, this is a very good question. And in addition to the language model, and I think it's also important to highlight that we also speak through a history of diagnosis today when we think about how this is actually diagnosed, because I think it's very important to highlight that even today, the diagnosis of pretty much all cancer types is really done under the microscope from a pathologist looking through a microscope on a tumor tissue. And I think this is very important because this is also how historically we had the development of histological classification, which have really changed over decades from earlier diagnosis from this is a lung cancer to much more refinement that we have today. And while I will speak probably also a little bit about the more complex molecular tests that we are doing, I think we see already in the name of small cell lung cancer where the diagnosis is actually coming from. And you might still hear this in many other lung cancer diagnoses. We have a squamous cell carcinoma, we have an adenocarcinoma, we have a small cell lung cancer, which is really highlighting that still the shape of the tumor cells that the pathologist sees under the microscope is really something that is very important to ultimately establish the diagnosis that we have there. And as profound as it seems, so small cell lung cancer is really typically defined by the presence of relatively small tumor cells. I say relatively because these are usually in comparison to other cancer types that you would expect there. But there are also many other parameters that a pathologist can take into account when looking at those tumor tissue under the microscope. So what you hear often is, for example, the composition about the tumor microenvironment that we see there. For example, do we see that the tumor has what we call necrotic tissues? This is really where like tumor cells are, so to say, dying. Do we see parts of the tumor that are separating? We call this mitotic areas. Do we see a lot of cell proliferation that is happening there? But generally, the first layer is really to look at the tumor composition and the shape of the cells that you're having there. Of course, this classification and methodology has massively evolved over the years, and today we have much better tools to really classify and diagnose and establish diagnosis of small cell lung cancer, particularly through a methodology that we call immunohistochemistry, or IHC, just to put the word out there because many of your patients might have heard this, which is really a methodology where we can specifically stain certain proteins within the tumor that we know that are associated with, for example, small cell lung cancer. And today, this is really the backbone, not just for small cell lung cancer, but also for other cancer types and lung cancer, but also other types, to really establish with a high certainty that this is a certain cancer, like, for example, a small cell lung cancer. So the important summary here is that what we're really looking at is we look at the tissue. So typically we really have to see what is the tumor tissue that we have there, of course, together with the whole clinical diagnosis. And then we use those immunohistochemistry and some other methodologies that we use to establish the diagnosis of small cell lung cancer. That being said, and I think this is also important to highlight here, these methodologies are evolving. And the more we learn about the cancer type, the more we're moving from a morphological diagnosis into something a little bit more biologically informed. So when we speak about non-small cell lung cancer, what your patients might also, for example, hear is it's a neuroendocrine carcinoma. And probably we'll speak about this later, but there might also be small cell lung cancer types which are non-neuroendocrine carcinoma, which are established by the methodologies that we're having here. And now much more, we see that we look more at profound and biological features within the cancer, like certain what we call transcription factors. Like, for example, does the small cell lung cancer express ASCL1? Does the small cell lung cancer express PAU2F3 to kind of increasingly refine the diagnosis of small cell lung cancer that we are having here? So again, you see, we are going into a little bit of a transition where we're getting more and more molecularly refined, but I think it's still important to highlight that the diagnosis is still somebody looking through the microscope or digitally at tumor tissue and at the tumor types to really establish the diagnosis of small cell lung cancer.
Thank you, Dr. Heeke. That's such an important and really elegant summary for our listeners to hear about the diagnosis and why it's important to just look at the cells, right? And to do the additional testing. And this is why the pathologists need a little bit of time to make sure we get the right diagnosis, because if we don't, that might put us on the wrong track, the wrong treatment, the wrong follow-ups, the wrong, line of therapy for our patients. And really, we want to make sure this foundational portion is really 1000% accurate. And Absolutely. This is where these other tests, and sometimes, as you mentioned, that like those non-neuroendocrine small cells can really make us scratch our head and say, wait, what is this? And that might be something where we see those PAU2F3 positive cells or triple negative cells, and that those also deserve additional testing and really careful diagnostic tools to make sure that we get the diagnosis for our patients right. Diving in a little bit further, so again, this is really laying the foundation for the rest of our talk. What are biomarkers? I know that biomarkers testing can sound really complicated, and even for our residents and our fellows, they say, "Oh, biomarker testing is done." Or maybe it wasn't. Maybe it was something else, right? Can you talk about biomarkers? Does every cancer have biomarkers, and why do they matter? I know this is a very loaded question, but can you give us kind of an overview of what are biomarkers?
No, this is very great, and I like how you mentioned it. Like, what's biomarker testing been done? What does this even mean? Because a biomarker is a very broad term when you think about it. I think the easiest is to say it's a a biological characteristic that we can measure. I think what is really important is that it's something measurable, that we can really understand biological functions. But a biomarker can encompass many, many different parts. So right now we spoke about diagnostics, for example. So certain, like I was mentioning, like immunohistochemistry staining, for example, maybe we stain for one of those neuroendocrine or small cell lung cancer specific proteins. So this is a diagnostic biomarker, a biomarker that supports the diagnosis of small cell lung cancer. But when we speak about biomarker testing, this can mean a lot of different things. For example, we can speak about predictive biomarker. A predictive biomarker is something where we measure, again, something biological, then we can attribute a treatment to it. It's predictive of a treatment. The probably most known one, especially in lung cancer, is, for example, the presence of EGFR mutations. Many patients in non-small cell lung cancer, or a certain amount of patients in non-small cell lung cancer, have specific mutations in genes like EGFR, in a gene like KRAS, or what we call gene fusions in genes like ALK or RET. And these are interesting because when we test them, for these or for most of these alterations, we have a specific treatment that if, for example, you have an EGFR mutation, then the medical oncologist could say this makes you eligible for a certain treatment. So these are predictive biomarkers, which I would argue are probably among the most important ones because these really allow us to shape how we are treating patients. There might also be, and I think this is getting increasingly more important, are biomarkers, for example, for toxicity. We know that many of the cancer therapies that we are having can be associated with certain toxicities. And the idea of can we predict them, can we measure them, can we find a way to detect them early, to attribute to it, is also something that I think is very important. And we see increasingly more the development of those toxicity biomarkers, especially in small cell lung cancer, where we have very novel therapies that we are trying to understand. And then lastly, I think what is also important is that we also use biomarkers just to measure the cancer intrinsic processes that even after you have diagnosed the cancer and you have characterized the cancer to initiate the right treatment, we can now use biomarkers to follow the cancer as it develops, as it evolves, as it grows, shrinks, and do this over time and follow, so to say, with our biomarkers, what is happening within the tumor and get more insights to ultimately adjust the treatment. So I think it's important when somebody says, oh, we have to do biomarker testing. What does it actually mean with what was tested? What is the biomarker? And what is the purpose of the biomarkers that was tested?
This is absolutely fabulous. And I think, all the medical personnel that might be listening in or researchers, again, these distinctions are really key because when we're thinking about diagnostic biomarkers or toxicity biomarkers or predictive biomarkers, the context matters here. And it's really important that for when we're caring for our patients and we're being thorough, that we make sure that we have the right biomarker in context to the patient, right? So absolutely key. Thank you for distilling that down for us. And I know that, you are a true world-renowned expert in liquid biopsies, right? You have led international committees. You've been at the forefront of the establishing, creating, and bringing these to the bedside for our patients. So, can you first tell us what is a liquid biopsy? What are we talking about when we say a liquid biopsy for patients?
So thank you very much, and I'm much more modest than you were saying on my contribution to it, but I appreciate your kind words. So I think most of your patients are familiar with the biopsy, which is a way to get access to tumor tissue, for example, as we spoke in the beginning, that we need to establish, for example, the diagnosis of small cell lung cancer. And typically when we speak about those biopsies, the idea is really to get access to tumor tissue, to tumor-derived material that we can test. A liquid biopsy is I wouldn't even call it a new concept because it's something that is around for a long, long time. Actually, we know, or let me first speak about liquid biopsies, and the concept is that instead of getting direct access to tumor tissue, is that we use liquid components that are typically more easily accessible, less invasive, to use these to get access to tumor-derived material. When I say liquid components, you see it's a very broad term. So what we're typically speaking of, and I think for the most of the time during the talk, we speak, for example, about blood. Because of course, when we have the cancer needs access to the blood, because a cancer is also a living tissue which needs oxygen, nutrients. And the idea there is that this might lead to a collection of tumor-derived material within our bloodstream. And that when we now just take a blood drop or take blood, that we can now get insights from the blood that we are having there to also understand what is happening inside of the tumor, equivalently or even better than if we would just get tissue, or if we would get tissue directly from the cancer. I still say liquid components because I think it is very important to highlight that we can really utilize much more than that. So we can use saliva, we can use cerebrospinal fluid, we can use, for example, quite frequently for patients with bladder cancer, urine is used as another methodology to get to use liquid-derived material to get insights into tumor tissue. And the important general idea is that taking those liquids is typically considered to be less invasive than if we get to a tissue biopsy. And hopefully this allows us much better not only to understand what is happening within the cancer, but also allows us to do something very importantly, which means that we now can follow the cancer multiple time points. Because getting a tissue biopsy, of course, it's something that we really want to minimize only when it's needed. So to say, it's a very invasive procedure. While taking blood, I wouldn't call blood as non-invasive. Sometimes people say liquid biopsy is non-invasive. I wouldn't say this, and even taking blood can be for many patients really not the easiest. But it's still something that is much easier, so to say, to get access to it, and now allows us to follow over time and better understand what is happening inside of the cancer and follow, so to say, what is happening in almost real time, but more importantly, really allowing us to get multiple time points to better understand and follow with the therapy what is happening inside of the cancer. So this is the general concept of liquid biopsy, which applies to pretty much all cancer. So it's not just a thing that we do in lung cancer, a thing that we do in small cell lung cancer, but it's definitely something that has drawn a lot of attention in small cell lung cancer particularly.
Thank you, Dr. Heeke. And I think, when we're thinking about these tumor analytes, we're really thinking not only DNA, but also other components, right? Like RNA. And I know you studied a lot about methylation and then proteins and specific classifiers. Can you kind of focus a little bit more on what are those components compared to like what we hear about circulating tumor cells? Are those the same thing?
So the first important thing is let's think about what we're looking at, and let's think about how the cell composes. So when we think about a tumor cell in itself, it contains a lot of different material that the cell needs to survive. So we have the DNA, which is the genetic information where we can see, okay, how are certain mutations. We know that the DNA usually gets transcribed, what we call it, so changed into a molecule that we call RNA, which is kind of a messenger molecule, which tells us what are actually those genetic components inside of the cells that are currently active and that are currently required by the cell to produce the next analyte, what we call protein, which are kind of more of the building blocks that are exhibiting the biological function. This is something that happens in all cells, but of course also in tumor cells. And the important is, once a tumor cell dies or gets destroyed, then this material gets, so to say, brought outside, get released into the bloodstream, and all of those different components can then be analyzed. In contrast to this, when we speak about circulating tumor cells, and I was mentioning liquid biopsies is not a new concept in the sense that we know about circulating tumor cells since the end of the 19th century. So it's by more than 100 years that we know that there are tumor cells floating in the bloodstream. But these are very interesting because these are really living tumor cells. And the important thing is when we look at circulating tumor cells is these are really tumors that is possible to exhibit a biological function. This might lead to metastasis. These are really cells that when we get them out, so to say, when we're able to extract them out of the blood, and there have been many research teams which have been very successful, we can even take these cells and, so to say, grow them in our laboratory. For example, if we want to study it, if we want to see if we can personalize therapies. So this is very important when we think about the circulating tumor cell. Well, when we look at the other components, DNA, RNA, protein, these are the components inside of the cells, but we take them out of this biological construct of a cell. So this makes them typically a little bit easier to look at. For example, extracting DNA out of a bloodstream, which was a technical hurdle probably 10 or 15 years, is a very straightforward process. When you would hire somebody new at your laboratory, pretty much by the first day, these people would be able to extract DNA out of the blood and start to analyze it. So I think it's really important to see what do we actually want to do. Going a little bit from small cell lung cancer, because we had the example of EGFR mutation, for example, in non-small cell lung cancer. If we want to look at an EGFR mutation, then it's typically sufficient to just look at the genetic material, so to say the circulating DNA, and see if we detect it or not. Well, again, if we want to have much more functional analysis, then typically it might be better to study circulating tumor cells. What is important, and you hear I can speak for way too long about this, so to summarize it a little bit, is really it depends on what we want to look at, because all of the material that we can get from the tumor can help us to understand, and all of those different materials can help us to shape different questions. Some might be more interesting for shaping clinical treatment, some might be more interesting for understanding the biology, but we typically try to really take the totality that we have there and make sure that we have the right material for the right question.
Thank you so much. Thank you for summarizing that and really clarifying. I know that this is a big misnomer when we hear, oh, CTCs, oh, ctDNA, oh, ctRNA, cell-free RNA, cell-free DNA, and it can be, as mentioned, we need a language guide to really distill down what are we looking at and what component. And when we hear about tumor fractions and DNA, what in the world are we talking about when we see sometimes these reports or our teams talking about it? So thank you for highlighting that. So, I think we could have a whole separate Smashers talk about your research, right? Easily. But, can you give us a glimpse into some of the things that you've discovered, your research focusing on detecting these tumor biomarkers, right? Can you kind of explain some of the novel ways that you've used and the tools and the technology you've employed? Can you just give us a peek into your research? I know we could chat for hours about all the things you've accomplished.
Oh, of course, and please interrupt me because I like to speak, so I don't 3 hours speak about my research, and I've also tried to highlight some other research there. I think generally there are two components in the concept of small cell lung cancer, which I think are very important. And you kind of mentioned this already. So the first component is, like you were saying, and what probably many patients have seen already is like variant allele frequency, tumor fraction, ctDNA. What does this mean? So the first question I would argue is, can we use liquid biopsies to track how much cancer is there, to speak very broadly? Because I think this is very important, because this will allow us to understand, like, if there is a new treatment, oh, is this treatment destroying tumor cells that we want to have? So do we see a decrease in the amount of tumor material that is shed into the bloodstream, which is typically really very nicely correlated to the amount of tumor that is present, highlighting, oh, perfectly, we see the amount of tumor is going down, highlighting that the treatment is working. Or after a treatment, we see it seems like there's still this circulating tumor DNA. So this DNA derived from cancer cell is still there. Does this mean that we have to think about additional treatment? Or conversely, we no longer detect any circulating tumor DNA? This means that probably we have destroyed the tumor, which is kind of the aim of the therapy. So I think one question is like, really, can we use these materials from liquid biopsies to better track what is happening inside of the tumor once we start and initiate treatment? This is something that I think is very important, and it's getting much more clinically focused, and it's getting much more clinical implementation. And we see this much more frequently used really in a more clinical environment. The second part, I think, is much more specific to small cell lung cancer. It goes back to a question that we had at the beginning about what is small cell lung cancer. Because many of those liquid biopsy methodologies that are used across different cancers really right now to track specific mutations. With the example of EGFR mutations, or for example, ALK gene fusions in non-small cell lung cancer. We can also think about BRCA mutation in breast cancer, for example. And we typically can really specifically look at these mutations that we know are specific to the cancer, and then use them to very nicely track actually what is happening inside of our cancer cells, because it's very different than what we see, for example, in our healthy cells. So small cell lung cancer is very particular in the sense that typically we don't see those mutations. Quite contrary, like what I was mentioning in the beginning, is we see that small cell lung cancer has much more different, I call it transcriptional states, where we see that the transcriptome, which is the genes that are transcribed that are giving rise to certain proteins, is very different between certain small cell lung cancer subtypes, despite that the mutations that they are harboring are actually typically relatively similar. They're not quite similar, but they're relatively similar. So when we now would just look at the DNA and we want to look at certain mutations, then we would miss what is actually happening inside of the small cell lung cancer. And this is very important. In the beginning, I was mentioning we have those transcription factors. And this might be something that your patients will increasingly hear. Oh, you have a high ACL1 expression, the PAU3 expression. These are not mutations. These are genes that are active or non-active. So we need specific methodologies to actually understand and track them. Meaning that we cannot just look at the DNA in itself, but we have to find surrogate markers to understand what is happening there. I think generally in the field, there are two methodologies which have been developed in the past years that are commonly used. The first one is DNA methylation, and the second one is a methodology called chromatin immunoprecipitation. So DNA methylation is something that I was working a lot on it, and it's the idea that while our DNA have those mutations that we hear about, there are tiny changes that are given to our DNA, which we call methylation, which are actually highlighting if this part of the DNA is active, so meaning that this part of the DNA will be translated into a protein, or if this part of the DNA is actually not active, meaning that this is something which our cells currently doesn't need, so it is stored somewhere else, and we don't need to look at it. So methylation is a very elegant way to better understand what is actually happening inside of the small cell lung cancer, to define what are the states that we are having there, but also to define changes in the states that we are seeing. And I think this is very important. I'm pretty sure we will talk much more about this, and you had this in other topics, is that this cancer might also change. So we need tools that not only allow us to make a snapshot at a given time how is the cancer, but also to understand how and in which direction is the cancer changing. Because when we understand that, then maybe we can engage with therapies earlier, or we can change a therapy to better understand what is happening here. So DNA methylation is one of these methodologies, which is probably a little bit more of the older methodologies, but clinically relatively broadly understood and is increasingly used in the clinical concept. So there are companies which are really using these already, for example, for the detection of different cancer types. And it's really a very nice methodology. And for example, we try to use it a lot to understand small cell lung cancer subtypes, but also, for example, Caroline Dive in the UK has really led seminal work in understanding how methylation can give biological insights into small cell lung cancer. The second technology, and I say this as somebody who spent many, many years using methylation, so I say this as somebody who's increasingly excited about some of these new methodologies that has really demonstrated massive impact in small cell lung cancer. It's CHIP, how we call it, a chromatin immunoprecipitation. So in addition to the methylation, which changes the DNA, our cell is also trying to change how our DNA is stored inside of a cell. Because when you think about it, like one DNA molecule in a cell is roughly 2 meters. So we need specific methodologies to really store this tightly packed inside of our cells. And you can think about if there's a part of your DNA that you need because you want to make a protein out of it, this needs to be more accessible. While other parts of your DNA that are currently not used, you can just store them together like a little bit, in your basement. You just throw everything there, and you don't care if you can go there. Maybe you have to put boxes away to go to the box in the bag. But things like in summer, like the summer shoes, you want to bring up, and you have them right next to your door. And the same way kind of is our DNA organized in the sense that things that need to be more accessible are differently stored by those chromatin states than things that are probably less active. And this is really a methodology which we can now use. There are certain modifications to it which tell us if this part is active or non-active to really get very good insights to understand the biology of small cell lung cancer as well. For example, Anish Thomas's team at the NIH has done really fantastic research which showed us how we can use this methodology to understand biology. And just, I think, a couple of weeks ago was a really exciting preprint which came out by Matt Osos and Sylvan Becker's team from the Dana-Farber, where they really used this methodology not only to understand small cell biology, but, for example, to track changes in small cell lung cancer states under therapy with, for example, tarlatamab, one of a more frequently used therapy option in small cell lung cancer. So I think these are the two methodologies that we're using, but without, so to say, confusing now everybody listening, like what does it mean? Is one better than the other? Which one should I use? My doctor gave me one, but I want to have the other one. It really doesn't matter. It's just two different methodologies which showcase technological development, which are really used to understand and get biological insights into how small cell lung cancer behave and changes under therapy. And I think this is the important message that I want to give it, that we have methodologies that allow us to better understand this. And these methodologies might change, might evolve, get better and more effective in really understanding the biological implications of small cell lung cancer and how we can ultimately use it to adapt treatment to it.
I absolutely love that. Isn't that great? And the shoes in the basement and the shoes at the front door. I'm going to steal that. That's fabulous.
Lisa.
That was a great analogy. And this is so fascinating, Dr. Heeke, and it's mind-boggling to me at how rapidly that the scope of this is changing. And I think back, many of the concepts that you have been discussing and talking about liquid biopsies, we followed hematologic malignancies like this for many years, right?
Yes.
And for our solid tumor patients, that has just not been a possibility. So as you have described so well this research and these methods, I'm wondering if you can just deep dive a little bit more for our smashers so they could really understand, can these liquid biopsies in small cell capture these changes in real time? Are there things that you would look for specifically that might tell us that the tumor is responding to therapy, or is it becoming resistant to therapy? How does that work in real time for patients who are undergoing therapy for small cell?
Absolutely. And again, I think there are two components that I also wanna highlight and separate. So the first one is what I was mentioning, tracking the ctDNA or the totality of tumor-derived material. Let it be ctDNA, let it be RNA, let it be circulating tumor cells. I think this is a concept which right now is relatively well established, but we know that when we see a drop in the amount of tumor-derived material that we can extract out of the bloodstream, that this is really correlated with a decrease of tumor material. We have increasingly sensitive methodologies that, for example, when we no longer detect tumor-derived material, we're getting increasingly comfortable to say that probably there's no or only very, very little tumor left, and that this is really something that we know is very prognostic for many, many cancer types, including small cell lung cancer, and that we can really use this measurement to better understand what is happening there. In the same way that when we see, and which we all know, which might unfortunately happen, is that when a cancer might grow back, that we even can use those blood tests to even see earlier that a cancer might grow back. Before we see it, for example, radiographically, we see that there's a new mass happening, that we even see sometimes an increase from the blood, which can be weeks, sometimes months before we detect it radiographically, but that this really highlights that a cancer might start to become resistant or that a cancer might start to grow back. And we see increasingly clinical trials that even use this methodology and adjust the treatment even before we see the radiographic changes. These clinical trials are not yet happening in small cell lung cancer, so I want to be very transparent here. But the concept that is happening in other cancer types that we've seen really highlights that checking how the tumor fraction, how the shedding of tumor material in the blood can really give us a very good surrogate to what is happening on the size and the mass of the tumor in response to treatment. I think this is something that we see increasingly common in many cancer types, and it's a concept that has also shown to be relatively, I mean, I'm not trying to be, putting in a relative, but a concept that is true in small cell lung cancer, where we see that this correlates to cancer. The second part is the understanding of biologically intrinsic processes, which I think it's important to highlight that right now we're at a stage where we use this in research projects. And I think this is very, very important to highlight. So we have seen that in the research project that this might really be a biomarker that can help us to understand how is the tumor changing upon treatment, and that this might even be a biomarker that can show us, for example, if a cancer type not only becomes resistant, but how does it become resistant? For example, to showcase the work from Matt Osa and Sylvan Becker team, for example, they could demonstrate that in patients that are treated with tarlatamab using this methodology, they could track that the small cell lung cancer goes away from what we call an ASCL1 high state, which is one of the transcription factors, just to put it there, into a state where the tumor relies more on the activity of another transcription factor, NeuroD1, and that this is associated with resistance against, for example, tarlatamab treatment. Again, I think it's very important to highlight that these are in a research setting, so we still are working on better understanding these, but I think it's very promising because it highlights, and it consistently highlights across different teams and different methodologies, that these methodologies can really be used to understand the biology. That being said, understanding the biology is the first part. So once we understood the biology and we understand that, for example, we see changes in the subtype of our small cell lung cancer under certain treatment, now comes the important second part, and this is understanding what is now the right therapy. Because I think what is very important for these biomarkers are a tool. But a biomarker is not something that changes treatment. It's the medical oncologist, it's the clinical care team, which decides the medical treatment based on biomarker information, but also many other information. So I think it is very important to understand that while we work, and people like me, for example, I work exclusively on the biomarker side, that it's very important that we don't only need to develop those biomarkers, but also need to understand that once we use them to understand biology, how can we use it to get a better treatment and align now the next line of treatment, for example, according to what we see inside of the tumor. I think it's very important to highlight. We see very promising research going in that direction. We now, for the first time, biomarker-guided clinical trials in small cell lung cancer, where we are really trying to use these and leverage these information to better understand how we can do that. And I think this is really how right now we see utility in those biomarkers. So first, to track tumor size, to see if we can, for example, if we successfully eradicated a cancer, or to see earlier if a tumor comes back, which is the first part, and I would argue the much more established part. And then the second part, which is inferring biological information about what is happening inside of the tumor. How can we attack the tumor because we know that there are vulnerabilities? How is our tumor changing to treatment, and how can we use it to get a more effective treatment subsequently if, for example, unfortunately, one treatment is no longer working? These are the two big parts how I think we really want to use these liquid biopsy biomarkers right now to better understand or to improve our caretaking for small cell lung cancer. And again, some might be in a more research state, some might be more in a clinically established state, but very importantly, there are many, many people out there who are really working and bringing them forward. And you were mentioning the speed in small cell lung cancer. I myself am shocked positively how quickly small cell lung cancer has evolved in the past years, where even I spent years to develop biomarkers for treatment, but got completely overrun because there were new and better treatment, which forced us to change our biomarker strategy. And to be really honest, I think this is incredibly exciting because this is what we want to have. Like, this is the situation where if you are out 1 week on vacation, you come back and you spend the first 2 days just to read what was happening while I was out on vacation, and how can I, for example, as a biomarker person, now contribute to it and help to build better biomarkers. I think this is very, very important. It's a challenge for us because we have to keep pace with what is happening there. But I think this is the best situation that we can have, that really, have so many clinical trials pushing forward, changing completely the landscape in small cell lung cancer. And now we just have to ensure that our biomarkers help us to bring the right treatment to the right patient.
That is so very true, and that is a great segue into sort of this last question I have about the biomarkers and the liquid biopsies before we transition here. And that is, the science is moving so fast, and you do need a few days after being out of the office to catch up. So What do you really see as the major challenges of moving this into sort of standard of care in small cell? And then what gives you the most hope in this research in small cell?
Now, these are very important questions. And I think it's also always important to highlight some of the limitations. And because sometimes you might hear, oh, I saw this research and why can't I get this when I get the treatment? Why does it take so long? This came out 6 months ago. Why is it not yet available? And I think first on the limitation, I think there are two parts. The first part are the technical questions. And I myself a little bit surprised to say this here, but I think the technical challenges are getting increasingly better. Like many years ago, everybody was speaking about sensitivity. We were always saying, like, how can we capture those tumor-derived material in the bloodstream? Like a normal human being has like 5 to 6 liters of like blood. How can we detect those tiny fractions of DNA, this search for a needle in the haystack that we are having there to really see what we can do there? And interestingly, we have so good methodologies these days that I'm not sure how much of a technical challenge we are really seeing there. There's one particularity in small cell lung cancer, for example, that I want to highlight is the most sensitive methodologies that we have are really personalized methodology. We call them tumor-informed, where we sequence using whole genome sequencing the tumor of each patient, and then use this to build a very personalized assay, which absolutely high sensitivity to really track what we are having there. In small cell lung cancer, I think many people know we sometimes don't have enough access to like tissue that it can build one of these. So we have to use a different methodology, which we call tumor agnostic, because we don't need the cancer there. And for many years, it was always a question, how sensitive are those methodologies? I would argue the newest methodologies that we've seen there have reached really good sensitivities. And while we can always claim that it can be better and it should be better, I think what we see technically right now is really good already to inform or to give us more clinical insight. So I think technically we're getting in a state where I would argue we understand the limitations, which is important. We work towards the limitations. And this allows us to better understand how we can use those biomarkers. So I think this is a good situation. If you would have asked me the same question 3 years ago, I would say like technical limitations. Right now, what I feel is getting more of a limitation that I see is no longer the technical limitations, but are the clinical implementation questions. Because like I was saying, like what we really want to do is that we have a biomarker which guides treatment. And in order to tell us that a biomarker guides treatment, we have to do the studies where we demonstrate that said biomarker is good for whatever treatment that we're having there. And while the technical advancements is very fast, sometimes 6-7 months, we have a new assay which better sensitivity, and we can validate these very quickly in retrospective analysis. Demonstrating clinical utility in a biomarker is something that takes very long time, because this is where we have to develop clinical trials and clinical studies that we have to do. It takes much longer to prepare those clinical trials, and it takes much more time to have a readout of those clinical trials. So I think right now what we are seeing is, and this is the positive side, is we see much more of those biomarkers being transferred into clinical trials. Sometimes, for example, we have the SWOG PRISM trial where we use biomarkers prospectively to stratify patients based on the subtype of their small cell lung cancer. But we also see more and more of those biomarkers being used retrospectively from clinical trials, which is not the best standard that we have there, but it's still informing us what we can use in the subsequent clinical trial. So I think it is very important to highlight in this concept, especially here speaking on this webinar for the patients, is that it's very critical to take those technical solutions that we have and transfer them into a clinical solution. And this, unfortunately, takes time. There are many hurdles that we have to overcome. We're really working on it. But just to highlight, this is why something that you read about 6 months ago might not yet be there. And I think this is increasingly becoming a bottleneck. This is kind of the limitations, and I want to use this in the same way as you were asking about hope. I think the hopeful part of it is, while we are aware about those bottlenecks, we see how exciting people are working on it. And we see how like 5, 6, 7 years ago, nobody would ask about a biomarker in small cell lung cancer. It's like, why would you do this? We don't need this. Now, every single discussion about clinical trials that I've been to is the question, what are the biomarkers that we have to look at? Do we need to include liquid biopsies? What can we do there? So we see that we have the awareness everywhere, on the industrial side, on the academic side. We have awareness with many patients who come in and ask, are there biomarkers, are there liquid biopsies that are being tested? Which I think puts a lot of pressure on us as researchers to really make sure that we find answers to the question that we are having there. And the second part that I think is very important in this, because even we don't know the answer to many of those questions. What I've seen as somebody who's worked in different cancer is probably the most collaborative cancer type or cancer field that I've really seen. You see this here in small cell lung cancer. Everybody talks to everybody. Like, we are really seeing this as a challenge that we want to tackle together to work on it. I remember there was a couple of years, like 2 or 3 years ago, we were all working on this liquid biopsies, and of course we all want to be the first, we want to be the best, and we want to highlight what we have there. But I remember we were at a small cell meeting in New York, and we were all sitting together having dinner at a table, and just, super excitedly speaking about the technology the other person was developing, and we were just there and chatting, like, hey, how can we bring this together? Like, hey, my technology has this limitations and your technology has that limitation. You know what? Let's just do it together. Let's just put it together. Let's work together. And I think what really, really brings me hope is seeing how this whole field collectively has decided that we need biomarkers in small cell. We need biomarker-driven clinical trials in small cell lung cancer. And we just have to do it all together to find an answer to those questions. I think this is what really makes me hope. When a field is so united in bringing new therapies, new solutions to the problems, to the clinical problems that we see there, then I think this is an unstoppable force. And I'm very enthusiastic to see where the field will be in the next 3 or 5 years, really working together. But this is what really brings me hope, is seeing how everybody is working together to find novel treatments and ultimately cures for small cell lung cancer.
Absolutely love that. And I couldn't agree more. This is, for any of our smashers listening in, our small cell research community and small cell investigators, translational investigators, is such a tight-knit group. We're all calling on each other because really, truly, this is a tight-knit community working together with patients at the center. And we're so grateful for all the work you're doing, Dr. Heeke. I do want to take some time. I know that we are running close to the hour, so I want to dive in and make sure that we talk about neuroendocrine subtypes just a touch more, and plasticity. Can we use, I know you mentioned some of these technologies to track the cancer. Can you explain what plasticity is and how that might shift a cell from one type to another? What does that mean?
Absolutely. I think when we speak about plasticity, then I think we speak about how do cancer cells behave and change. Because many cells in our body are what we call terminally differentiated. Like, we have a skin cell. This is a skin cell, and it will always stay a skin cell to do a certain purpose. But when we think about how our body is created, then we see that there's a lot of changes that need to overcome, for example, to turn something that we call, for example, a stem cell, which are cells that are not terminally differentiated, that can change into different cancer types, into those terminally differentiated cells that we are having there. So plasticity is a profound biological process that allows us to change the phenotype of cells, for example, to build organs, which is very important. In this concept, I think it is very important to highlight this, because this concept of changing one cell type to another is something that cancer likes to hijack for themselves, to change the appearance, to change the functionality there, and use this, for example, to avoid treatment. We have many, many different cancer types, and those neuroendocrine cancer, especially small cell lung cancer, is a cancer type that we typically see is very plastic, meaning it's a cancer type that is able to very dynamically change its phenotype, or which are the drivers, so to say, which make this cancer cell proliferating. We spoke a little bit about those transcription factors that are very important, and I think that are increasingly something which also our patients see as. So what we see, for example, is that we might have a small cell lung cancer, which is really driven by this ACL1 transcription factor, which is a really neuroendocrine marker. But what can happen, for example, especially when we put pressure on the cancer because we treat the cancer, then it changes its appearance and hijacks another transcription factor, for example, this NeuroD1 transcription factor, to now use this as the driver to continue proliferation. And this might mean that a treatment that is very highly effective when you have this ACL1 high state might no longer be effective. Now, small cell lung cancer is particularly challenging in this concept because you spoke about the neuroendocrine cancer. And for many, many decades, we always believed that small cell lung cancer is a neuroendocrine carcinoma, one of the typical neuroendocrine carcinoma. And then we spoke about this, and there's this other kind of small cell lung cancer. Now we have learned and understood that there's neuroendocrine small cell lung cancer and there's non-neuroendocrine small cell lung cancer, particularly this PAU2F3 subtype, which we now even believe might come from a different cell of origin within the lung. But we still call it small cell lung cancer. We treat it like small cell lung cancer, but it might be biologically a little bit distinct and uses different biological processes. The problem that we are having is that small cell lung cancer can change this. So even a neuroendocrine small cell lung cancer might become a non-neuroendocrine small cell lung cancer. And this is very, very challenging for us when we try to, for example, target therapies. How can we either prevent it, or how can we use a therapy that even if the cancer, so to say, decides to change its appearance, becoming more plastic, so to say, that we can also kill the cancer cell when it changes its appearance. So this concept of plasticity is a little bit where you have to think like the tumor is trying to change its appearance to avoid treatment, and we are trying to understand the appearance, probably even predict what the cancer is going to do, that we are a little bit this one step ahead. And unfortunately, small cell lung cancer is one of those cancer types which is particularly good in changing this appearance, making it much, much more important to better understand what is happening there. And I think in this context, it's also very important to highlight that there's a lot of fantastic research which came out in the past years, which really allowed us, using, for example, very specific model systems in the laboratory, to understand how and why a cancer might change its appearance through this plasticity process, where think about like clay, which you can shape in many, many different forms. And unfortunately, small cell lung cancer can do this very, very rapidly. So this is the concept of, plastic or plasticity that you might hear in small cell lung cancer, where the cancer type changes its appearance, and this might have effects on how a therapy is effective or not.
Thank you, Dr. Heeke, for highlighting that. I know we have one question in the chat. I promise we'll get to it. Last month we had Dr. Catherine Mader from MGH here talking about transformed small cell lung cancer. Can you touch on, for our smashers, and particularly we have our smashers who are part of our transformation tribe, if you could touch on, can we use liquid biopsies to detect or predict or study transformation or track it over time?
This is very interesting, and I think it captures a little bit what we had there. So first, I think we have to think about that we want to detect small cell lung cancer. And detection of small cell lung cancer, I think, is the most important concept that we're having. So we should detect small cell lung cancer, for example, as part of lung cancer screening. When you think about, can we detect small cell lung cancer early before we have the establishment of any diagnosis? But you were also mentioning what we see increasingly, I think, is this really interesting concept of transformed small cell lung cancer, where we have another cancer type, like non-small cell lung cancer, that is treated with very good treatments. This is probably one of the reasons why we see this, where now the cancer type, which was, for example, EGFR mutant non-small cell lung cancer, now becomes so plastic that it transforms now out of a non-small cell into a small cell lung cancer type, which is very important because this means that now you have to change the treatment from an EGFR mutant non-small cell lung cancer to a small cell lung cancer type. And the methodologies and the biomarkers that we are having, I think, are critical actually to do that. And I think especially in this concept, those liquid biopsies are actually critical to do that. Because right now, the way this is typically done is that you have to do a new biopsy. You see the treatment has changed and we don't know what is happening there. So it's like the beginning of a new journey that we started at the very beginning of this call. Like, we have to establish the diagnosis of small cell lung cancer even if it comes from non-small cell lung cancer. We need this diagnosis, we need this tissue biopsy, we need to have the pathologist looking into the microscope, we need to have the staining to then say, this is now small cell lung cancer, you have to adjust the treatment. Of course, if we can do this from liquid biopsies, then maybe we can understand this even earlier and see what we can do there. Because in line with this is another important question, is like, how different is it? Is it now small cell? Is it a transformed small cell? Is the biological process a little bit different? What do we have to look at? So I think this is something where we see a lot more interest right now. And positively, I think we see this much, much more also from the diagnostic sides, that companies are increasingly trying to develop those assays which can help there. And this is really very, very critical. The message is we want to detect small cell. If it's a transformed small cell, if it's a de novo small cell, if it's a de novo limited stage small cell, we want to detect small cell, and we want to detect it as early as possible. And if small cell lung cancer changes, then we also want to detect this as early as possible. And I think all the biomarkers, liquid biopsy, CTC, circulating free methylation, ChIP-seq, are all methodologies that can really help us to ultimately detect, characterize, and surveil small cell lung cancer to change the treatment accordingly. So yes, detecting transformed small cell lung cancer is absolutely critical, and I think it's something that we need to work a little bit more to, because it is really very, very important that once we detect it, that we can adjust the treatment accordingly. But I'm very optimistic that we see very good solutions very soon, if they're not already out there.
Dr. Heeke, this has been absolutely fascinating, and I think we could go on for another hour at least. But we did have someone, one of our listeners, commented about just how exciting that your research is, and that this is going to make a big difference in small cell in the future. And then we have a question from a listener that says, if treatment were to stop working, would it be prudent to ask for subtyping, and does that require a new biopsy? That is, until biomarker biopsy is available.
I think this is a very important question, and I think this is also where we have to be very careful in the sense of what I was saying is the biomarker need to drive a therapy. And in order to need to drive that therapy, we have to run clinical trials. So when we think about subtyping specific therapies, for example, these are things that are currently investigated in clinical trials. So to say, what this means is that if a small cell lung cancer therapy might stop working, I think this is something that then needs to be discussed with the treating medical oncologist to understand what is now the appropriate next step. And it should be then the question like, is it appropriate to make a new biopsy? Is there a clinical trial option that would leverage this? But I think it's very important that this is first always has to be done in discussion with the medical oncologist. I develop biomarkers. I don't develop therapies, and I don't decide what a therapy is given. This is something that the patient has to work together with the multidisciplinary team, of course, with the center of the medical oncologist. But there might be, when discussed with the medical oncologist, of course, there might be a clinical trial option that might be worthwhile then to, for example, get a liquid biopsy, get a tissue biopsy, get testing for subtyping. But I think it is really important to highlight that this is something that has to be done in the appropriate setting to ensure that the testing gets translated into a clinical option. Because if we just do the test and it doesn't change what we do afterwards, then it's probably not the right thing to do the test. So I think this is very important, that there are more decisions that need to be taken into account, whether this is the right biomarker or whether there's another test. This is important. So this is really something that I would give to Misty. I think you're for sure, Dr. Shields, you also have a very good answer to that, how you would approach such a question if a patient would come to your practice.
Thanks, Dr. Heeke. Yeah, I think that this is, definitely a patient and provider discussion. And really every time, just as a whole, when we're ordering tests, we say, what are we going to do with this test when we get that result back, right? And so that's where making sure that you have a plan A, B, and C as to what are we doing next with this information? Will it help make a decision for me? Those are the really important questions to bring to your team, because that's just good clinical practice, right? When we order a test, what are you going to do with it? If not, it's just academic. We don't want anyone to have any additional worry or anxiety or cost for something that isn't going to change their care and help them feel better. So definitely important to talk to your team. But I think, Dr. Heeke, you're leading the way in these efforts of trying to get these research from the bench to the bedside as soon as possible. So thank you for all you're doing.
Yes, Dr. Heek, thank you so much for joining us today. We know that knowledge is power. Certainly, our smashers and our listeners today have learned so much from this informative discussion. It's just really exciting to know where your research is taking us in the future of treating small cell lung cancer. Thank you to all our smashers and everyone who joined us and tuned in today. And please tune in with us next month when we speak with Dr. Charlie Rudin from Memorial Sloan Kettering Cancer Center. Have a great Friday afternoon and a great weekend.
Again, thank you, Dr. Heeke. Thank you so much for all your expertise and really just dedicating your professional career and your personal passions to our smashers. Again, thank you so much.
Thank you so much. It was an honor being here today, and thank you all for the great work that you're doing within this group. I think this is really critical. So it was truly an honor to be here today.
Thank you.
Thank you, Dr. Heeke. Thank you, our smashers. Have a fabulous weekend. We'll see you next month.